Hey, welcome everyone. To see you all, or two of you. How's it going? Um, plan today is to move on into our next topic, which is going to be relations and equivalence relations. And part of this is going to be building this idea of what a Cartesian product is. So you did a little bit of reading on that. So we'll go through worksheet 15 today. And then we'll start worksheet 16 a little bit, and then your reading quiz for Wednesday's class will be basically about the stuff that we talk about on worksheet 16. So won't be new stuff on the reading quiz, but mainly just a review of the stuff that we covered towards the end of today's class.
Real quick note, the quiz for today is labeled Wednesday, October 19th.
Oh,
that
okay.
really confused
Well, then
me for a few minutes.
I'll leave it open a little bit longer so people have time for that. Yeah, there was a quiz that was supposed to be set for Monday. Apparently, I might have closed it already.
I think all the dates and everything was right on it. It was just labeled Wednesday, and so I was very confused looking for it because I was trying to look for Monday.
I'll take a look afterwards. Thanks for letting me know.
Thank you.
Yeah. Any other questions before we get started? So you've got homework due this evening. Don't forget about that. And then you've got a new assignment that is up for next Monday. So the assignments are a little bit shorter, 4 or 5 problems, but they're proofs, so they might take a little bit longer. But we've got all of our proof techniques done for this semester. So now it's just kind of looking at different math universes where we can apply these ideas. Okay, so let's just kind of quickly review what was on the video, the quiz. So when we talk about our Cartesian product of 2 sets, it's a fancy word. It's just an ordered pair of products, or an ordered pair of points, essentially. So the first element in the pair comes from the first set, and the second one has to be an element in the second set. So these can be continuous things, like this example where we think about x going from 0 to 2, y going from 1 to 3, and then this would be this entire closed region over here. So this would consist of all points whose x-coordinate is between 0 and 2 inclusive, and whose y-coordinate is between 1 and 3 inclusive. And then in addition to that, we could also have a bunch of discrete ordered pairs as well if our elements are just a discrete group of numbers. Okay, and then, yeah, so one of the questions on the reading quiz, to ruin the surprise if you haven't looked at it, was related to question 2. And so in question 2, is this true or false?
False.
Yeah, so this is false. And here's a counter example, right? If we switch the order around, then suddenly we would get a totally different space over here, right? If we flip it around, then we're saying, okay, not quite. Right, now we're saying that x goes from 1 to 3 and y goes from 0 to 2, and this gives me a different rectangle. So the order does matter. Okay, so then let's think about some of these other examples. And then what I'd like us to, or for you to get to, would be to work on this one. But let's try one of these examples together. So now we've got induction, we've got direct proof, we've got contrapositive, we've got contradiction. So we want to be able to identify all of these proof techniques and which one might be appropriate for which setting. Okay, so this is a true statement. So this is a conditional statement. So we've got different ways that we might think about doing this. Okay, so if we kind of think about our techniques here, and which of these might be appropriate. Although we just learned this one, it's really nice once you get a new toy to want to use it for everything. It's not going to work here. There's no kind of show this property holds for all integers bigger than this sort of thing, right? Those are the types of problems when induction comes in handy. And we don't have any sort of statement like prove this is true for certain values of n. So we're going to have to use one of these techniques. And probably, you know, the most straightforward way of thinking about it is probably to do direct proof. So when I'm kind of thinking about this, that might be my first thought is how can I do this directly? And if that doesn't work out, then let me try some of these other methods. So let's do this by direct proof. So that means we're going to assume that this is true and then try and show that is true. And it's nice when we're writing these out before I use A, B, C, and D to explain what they are. So these are all sets. They're not numbers or anything else. They're not matrices. We're dealing with sets. And we'll assume A is a subset of B, C is a subset of D. And now we want to prove that A cross C is a subset of B cross D. And so this is bringing back a lot of stuff from the semester. So how do we show that one set is a subset of another?
You have to show that all of A cross C is in B cross D.
That's right. So we'd want to show that if an element is in A cross C, then it has to follow that it is in B cross D, right? So this is how we prove subsets. So now an element is not just a single thing, but it's going to be an ordered pair. So let me just say, like, this does not need to be a part of your proof. So I'll just write it in green. But sometimes it helps to write this out. If we have an element that's in A cross C, then it must follow that that element also is in B cross D. So if you're kind of looking ahead towards the conclusion here, right? That would kind of be the last thing that we're going to try and show is that, okay, therefore this thing has to be in B cross D, and then therefore we have that. And so then we can kind of work our way either from the bottom up or from the top down. So any thoughts on what we can do next?
I guess start with the suppose that xy is an element of A cross C.
Yep, so let's consider xy that sits in A cross C. And so if I want to show that xy is an element of B cross D, kind of what would need to come like right before that what should be true about X?
X is an element of B.
That's right. So if we've got X is an element of B, and I can show that Y is an element of D, then that's going to give me this next sentence here. And I'm just trying to kind of show you that we can kind of think to the end and then work our way back. So sometimes if you get stuck, that's a useful strategy.
So going back up to our start,
Yep.
if we consider X comma Y an element of A cross C, then X should be an element of A and Y should be an element of C.
Yep. So let's start there, right? So if XY is in A cross C, then we have X in A. Let's just deal with X first. And since X is in A, what do we know?
X must be in B because we know A is a subset of B.
That's right. So if X is in A, and A is a subset of B, this tells me X has to also be in B. So that handles that piece there. And then we would make the same exact argument for Y, right? And I can take this out now, and that bridges the gap. There's no logical step that would come in between that and what we were hoping to get in the end. So once I've shown that X is in B and Y is in D, it's pretty safe to say thus XY is in B cross D. And again, this sentence in green, you don't need to put in there. If you find it helpful, there's nothing wrong with including it. Any questions? Okay, so that checks off this one. I don't remember if I asked you this on quiz or not. What do you guys think about this statement over here?
I think it was one of the multiple choice options in something.
What do you guys think about that?
False.
Why is this one false?
It's not a ordered pair.
That's right. So this is just a bunch of numbers, whereas this is a bunch of points in the plane. That's right. So it might seem like this is embedded inside of there, but we're comparing apples and oranges. One is the set of real numbers. The other is a set of R2, like the coordinate plane. So this one is false. All right, so that sets us up for something like this one. And you've got, I don't remember if I asked the same exact thing. You have something very similar on homework, I'll just say that. So this is a good one to practice. And it's gonna be harder than the one that we did together. And some people have been saying like, hey, when we do things, you do the easy, that you don't have a chance to practice hard ones in class. So we'll try this one out. And the reason why this is harder, it's just because you've got inequality here. So that means if you call this, all of this stuff P and all of this stuff Q, remember that you're gonna need to show that P is a subset of Q and Q is a subset of P. So that's how we prove set equality. So actually, this proof is going to consist of two parts. You're going to say part showing P contained in Q, and then there'll be another part that Q is a subset or equal to P. Yeah. And if you finish up that one, then that's great. You guys can move on and think about 6 and 7. But let's focus on working on question 5 together, or at least in your breakout rooms before we talk about the others. But any questions before I break us up? Checked in with a couple groups. Matt was checking in with a couple groups. And over here, I just have a snippet from one of the whiteboards that we were working on, minus any math notation. I just typed this out. So here was one proof of showing the left side is a subset of the right side by starting with an element in A intersect C crossed with B intersect D. Then this would tell us that X is in A intersect C, Y is in B intersect D, right? Because we know that X has to be in here and Y needs to be in here if it's in the cross of those two. And then since X is in this intersection over here, this tells us that X is in A and X is in C. And we get similar conclusions since Y is in B intersect D, Y is in B, Y is in D. And the group that I was working with that came up with this then were wondering whether it's okay to go from this sentence right over into the next sentence. But let me kind of just stop here. Any questions? Okay, so then the question was, well, do we need to justify more if, oh man, how do we get back into my text box once I leave?
I don't think you can.
I just want to put an extra line break. Okay, anyway, that's not going to happen. So the question is kind of with this part over here. Let me change this to red. This sentence here that I'm underlining in red, since X is in A, Y is in B, then we've got X, Y in A cross B. I think that seems like a pretty direct result from the previous one, since the previous one was X is in A, Y is in B. So that's enough to claim that X, Y is in A cross B, and that's enough to claim that X, Y is in C cross D. And if it's in both of those sets, then it's going to be in the intersection of them. Okay. Any questions? Does somebody want to take me through the other way? I'm going to give up on the whiteboard for a second.
I just did it the same. Well, yeah, I can do it.
Let's see. We were.
Screen share isn't showing. It hasn't loaded for me.
So okay, here I want to show A cross B intersect C cross D is a subset of A intersect C cross B intersect D.
Yeah, screen share is not working for me. I'm
Yeah,
not seeing
it's not
the
working
screen.
for anybody. Don't worry.
Oh,
It's
okay.
not just you. Here you go. Okay, so we're on this one and we proved one direction. And so now we want to prove the right side is a subset of the left side. So how can we go through this one? Did the groups get, I know some of them got through this part.
We can assume.
Yeah,
We can start by assuming P.
by assuming,
The X cross B intersects C cross D, which means that X, Y is in A cross B, and XY is also in C cross D.
okay, so we're going to start with an element in the other set and kind of do the reverse here. So that means X, Y is in A cross B, and X, Y has to be in C cross D if it's in the intersection of those. Can you guys hear the outside? I don't know if that picks up. They're like, okay, good, never mind them. Okay, sounds good. You got the mic, Fossey, unless you want to.
I was like, would you like me to keep going?
You're doing great.
Okay. So from there I said, therefore X is in A and X is in C. And then Y is in B and Y is in D.
Y is in B and Y is in D.
And then I said, since X is both in A and C, X is in A intersect C. And since Y is in both B and D, Y is in B intersect D. Therefore, XY is in A intersect C cross B intersect D.
Great, thank you. Any comments or suggestions about how to make this better, or anybody do it any differently? Yeah, I think like this looks great. I have one very minor comment, maybe to make this flow a little bit better, not to correct anything, since this all looks good. But I think like if you make this comment over here, I think it makes sense maybe to say this right after that and say like, therefore X is in A and X is in C, so X is in A intersects C.
Yeah,
because
that
it
makes
follows
sense.
kind of more immediately that way. Then you can say, we also have X is in B, or excuse me, Y is in B, Y is in D, so Y is in B intersect D. But I think it flows just fine like this. Any other questions about that one? Did any groups get a chance to think about this?
We started on it, didn't really get too much into it.
On 6?
Yes.
Did you think it was true or false?
Uh,
I guess that was
true, yes.
part of the problem is what might not have been clear is the instructions before all of these were prove or disprove, and some of them are false and some of them are true. So that's part of the fun.
Yeah, we've just got to the point of figuring out the approach we were going to use, which was to show that it's true, but basically, yeah, you have to show that A is a subset of B and B is a subset of A to show that they're identical, which gives you the identical Cartesian products despite order.
So this is an if and only if. So you need to check, is this thing true? And if we flip it around, if this is equal to that, does that have to imply A is equal to B, right? Because this is a biconditional. So it's saying this thing implies that, and that thing has to imply that. And if one of these is true and the other one is false, then altogether the statement is not going to be true. And I will say one of them is true and one of them is false. So altogether, this statement is not true.
Okay, so because the second one, wait. No, I mean, you think, yeah, if A equals B, why would, okay, I'm confused as to why it's false.
Anybody have a suggestion?
Can we try to come up with a counterexample?
Yeah, let's try and find the counterexample. And when we're trying to do this, let's just think of really easy sets. Now, what's the easiest set that might come to your mind?
An empty set?
Yeah, and these are really good at doing counter examples as well, because the empty set is kind of a special thing. And we're trying to disprove this, so I don't want to pick, so I can either pick A and B that are equal to each other and show that the cross products are not the same. But this part is true. This is the part that's false. No, sorry, other way around. Yeah, well, let's see what happens. So let's pick just two really easy sets. We'll pick an empty set and we'll pick the set that just contains one. Let's see, that is not going to give us a counterexample, right?
How would an empty set map?
How would an empty set, sorry?
How would it map? Is that why it's false, because it doesn't map?
Yeah, how would an element from an empty set map to an element from the other set to give us an ordered pair?
So let's see, I think here's the idea here. What happens if I take these two sets and I take A cross B? What do you think happens when I take the empty set and I take its Cartesian product with like 1?
Don't you just get the empty set?
You would get the empty set back. Since you don't have any elements that could slot in for the first part of that ordered pair, that means this set contains no ordered pairs, right? And what do you think happens if I take B cross A?
Would you get the empty set again?
We would get the empty set again. And so here's a case where A cross B, B cross A are equal, but A and B are not the same. So we've shown that for this part of the biconditional statement, the hypothesis is true. Those are equal to each other, but the conclusion is false. So when you're trying to come up with these counter examples, like I said, you usually want to start with like a really simple case and then start to add complexity if it doesn't work out, rather than start to cook up like really complicated examples initially. And empty set is always something good to check out when you're trying to check for special cases or counter examples. Okay, so I'll leave this for you guys to think about and put up the solution to that. So the idea is it true or false then try and prove whether you think it's true or false.
Ask you a question about number 6.
Yeah,
So besides the empty set, would it be true?
besides the empty set, it would be true, yes. If you add this condition up here, if you say for A and B non-empty sets, and then you say this statement, then it would be true, yes. Okay, so I want to just talk a little bit about relations. And so in case you're curious, that section on the Cartesian product was way back in chapter 1. That was like the second section of the textbook. We didn't talk about Cartesian products when we were doing sets. I don't know why Siri is trying to answer a question here. And then we're going to take a look at.
It's no big deal that you don't know.
Okay, thank you, Siri, for sharing that. So then we're going to take a look at chapter 11. So chapter 11 deals with relations, and that's really the main point now. The reason why we need to go back and talk about our Cartesian product is because that's how relations are defined. So right now we're going to talk about relations in general, not just functional relations. So let me say that the textbook, when they define a relation, they define a relation on a single set in section 11.1, and then they kind of define this separately way back at the last section of chapter 11, where they say we can also talk about relations from a set A to a set B. The definition is the same. It's just thinking about whether my domain and codomain are the same sets or whether my domain and codomain are different sets. It doesn't change how we're going to define this. So I'm just going to define it in general where the domain and codomain don't need to be the same. So we're going to say we're going to map from set A into set B, and the relation is defined as a set. It's defined as the Cartesian product of A and B. And so we would say XY is in the relation R. And sometimes we shorthand that with an X and an R and a Y. So this is saying X satisfies this relationship with Y. And this all seems like very abstract symbols here, and I think it will help once we take a look at a couple of concrete examples. And we use this R with a slash through it to denote that X is not related to Y. And so each of these things are statements that might be true or they might be false. So for example, if we just take set A to be 1, 3, and set B to be 2, 3, 5, and 7, then this set over here represents a possible relation. What this is saying is that the element 1 is related to the element 2. The element 1 is also related to the element 3. So this is not a functional relationship, but it's okay. It is a relation. So we don't have this idea that each thing in here gets mapped to only one thing in here. We're not going to impose that restriction on this. So when we read these points, this would say, well, here's A, here's B. This relation is saying that 1 is related to 2, 1 is related to 3, 3 is related to 5, and 3 is related to 7. So this statement 1, 3 right, this one would be true since 1, 3 is an element of this set R. We would say this statement is false since 1, 7 is not an element of R. And this last one is also true because 3, 3 is not an element of R.
So the relation is not necessarily every combination from our Cartesian product. It's just whichever ones they want.
Yeah, there is something called like the universal relation, which would be all of the possible relations that you could define. But yes, in general, the relation could just be one element. That's right. You can define it however you like. The only restriction is that the first element needs to come from set A and the second element needs to come from set B.
So yeah, so they need to be valid ordered pairs from the Cartesian product, but you can choose any of them as desired.
Yes. So,
Okay.
yep. And so one thing that you'd want to be careful about with this in mind, let's say I want to do it like this. So the idea is, okay, what about this relation 2, 5? Is this a true statement or false?
For the given relation, it is correct.
Yeah, so for this, it is true, right? You would look at this set and say, okay, is 2, 5 an element in here? And it's not because 2 is not even an element of A, right? So here we can see that this is true. And in fact, there's no relation that we could define from A to B that would have that in there, right? Because 2 is not an element of set A. So this example is just kind of like a random smorgasbord of like values and sets A and B that I just kind of made up out of nowhere. That's right. There's like no real logical way that you could try and describe what this relation looks like, as opposed to like saying, right, that's a much clearer relation between R to R. So I can think about this as a relation, and there's a rule. If I know what the first coordinate is, I can get a very specific second coordinate. So that's great. Sometimes we have these rules, and sometimes the best way that we can define a relation is to just list out all of the elements in the relation. So let me do one that's going to be similar to what you're going to have on the reading quiz. You can think about this as our little 5-minute video to help you with your reading quiz that we'll think about together. So let's say I've got this set A, and I'm just gonna go free form whatever numbers come to my head. Okay, so let's say we've got this set over here. And I want to define the relation So I want to define the less than or equal to relation. Okay, meaning I'm going to say X is related to Y if X is less than or equal to Y. So one way that I could define this relation is exactly that. I can define this in set builder notation. So I could say R is going to be the set of all things X, Y, where first of all, that's one way we could define that relation in using this set builder notation. And so now we're thinking about this as a relation from A onto itself. And this has the advantage of not having to write out every single element in here. Otherwise, we would have to say, okay, 2, 2, that's going to be in there because 2 is less than or equal to itself. And then I would have 2, 3, all the way up to say like element 16, 16. So that saves time of having to like list out every single ordered pair that would satisfy this relation. So I think on the reading quiz, I give you some relations like give me the greater than relation or the divisible relation or something like this. And I'm just gonna ask you, given that relation, which of these statements might be true, similar to how some of these went up here, how we did some of these. And this is section 11.1 of the textbook, if you want to read along with that. Okay, so I will stop here for the day rather than start something new. So next week, or excuse me, next class is, we're just going to work on this worksheet. So we'll work on the rest of the problems on this worksheet. Yeah, otherwise, have a nice afternoon. I've got a wedding in Arizona to go to virtually. So my father-in-law is getting married. So I will be heading there. First virtual wedding. I'll let you know how it goes. Hopefully it's a success. But have a nice afternoon. If you do have questions, the wedding is not until 5, so I'll stick around. If you have some questions, I'm happy to answer them. Otherwise, office hours tomorrow, or I'll see you on Wednesday.